I'm quite sure we will eventually win because when this wreck happens, that will be the end of the climate delusion, but it would be better to end it in a less dramatic way.
My guest today is Will Happer.
Well, thank you, Tom. I'm an old friend of Tom's, and he asked me when he heard I was going to Australia to give a series of talks if I would give a version of it on his podcast. So here I am. If anyone from Australia will run screaming from the room, to hear me again. But maybe there will be some who have not heard the talk, and so I hope it will be helpful for them. So I was asked to come to Australia by the Institute for Public Affairs and speak in a number of Australian cities about climate. Australia, just like many other countries, has a real problem with climate fanatics who have demonized CO2, which, our future generations will look back with astonishment at our time and wonder how it is possible that supposedly rational people could demonize CO2, but they have. And so what we've got now is a crusade against CO2. Crusades have been a curse of human history. Jihads, crusades, they have a way of ending badly, because people lose their senses, and the original alleged cause of the crusade or the jihad quickly get lost for other reasons that are less admirable. During the medieval crusades, the crusaders would shout, Deus vult, God wants it. And if you listen to the talk about climate today, it's apparently that God wants to get rid of all the CO2 in the Earth's atmosphere, which of course would kill all life on Earth. And so let's hope that the crusaders don't succeed. Now, none of us listening to this, or certainly I, are in favor of pollution. This is real pollution in Shanghai. You can see the poor resident of Shanghai with a mask on. It's not to protect himself from COVID. It's because of all of the smog in the air. You just barely see the bottle opener building and the Pearl Tower. And this is not CO2. It's not nitrous oxide. It's not methane. It's real pollution. And we wouldn't want that in any city that we live in. And so, of course, we're against this. But that's not CO2. If you can see it, it's not CO2. Here's my wife, Barbara, here not far from Princeton, where I'm giving this talk. And this green field is now completely black. They had just started when I took this photo a couple of years ago. And so what we're seeing is once wide open spaces, beautiful hills and valleys, covered with black solar panels or bird chomping windmills, wind turbines. So the actions being taken supposedly to save the planet are much worse than the alleged disease. This is really not a disease. And even if it were, the cure is much worse than the disease. Those of you who have not, I warmly recommend this classic book called Extraordinary Popular Delusions and the Madness of Crowds. And it was written by a Scottish journalist, Charles Mackay, I think first published in 1841. But what he said then was just as true today as it was then, that human societies go mad from time to time. If you worked for Bernard Baruch in the early 30s, when Bernard made a bundle of money by predicting the stock market crash correctly, before you could get a job, you had to read this book, and he would give you an examination to see that you got the main message of the book, which is avoid groupthink at all costs. And that's certainly true of any human infatuation. So here's if I can get this to advance, a quote from the introduction of the book, it says, in reading the history of nations, we find that like individuals, they have their whims and their peculiarities, their seasons of excitement and recklessness when they care not what they do. We find that whole communities suddenly fix their minds upon one object and go mad in its pursuit, that millions of people become simultaneously impressed with one delusion and run after it till their attention is caught by some new folly more captivating than the first. So if you look around any of the developed countries of the world too, you will indeed find millions of people who think they're saving the planet, by covering it with solar panels or wind turbines. In fact, they're doing just the opposite. And it's been very difficult to get them to stop and think about what's going on. So I'm going to try and tell you a little bit about why the science of Earth's climate does not support this. It doesn't support it at all. That CO2, this demonized gas, far from being a pollutant, is actually beneficial to life on Earth. And we should try and stop this folly as soon as we can. Now, I guess I should start by saying a few things about myself. I'm a physicist at Princeton University. I've spent some time at Columbia when I was younger. But as part of my professional work, I was a co-author of one of the very first books on the effects of CO2 on climate. This was written in 1982, before a lot of present climate scientists were even born. And there were a number of good people here. Half of them are in the Academy of Sciences. And we got the same wrong answer as everybody since. We estimated that doubling CO2 would increase Earth's temperature by about 3 degrees Kelvin, 3 degrees centigrade. And I can tell you, since I was there, this was simply a guess. There was no hard science behind it. It was the answer that everyone else was getting. So it was groupthink, exactly what, Bernard Baruch warned against, and we fell prey to it. In some defense of myself, part of the reason I didn't protest more, I remember being uncomfortable at the time, was I was working simultaneously on something I thought was more important. And so let me tell you about that. Again, this is to give you some feeling that you should listen to what I say about the science. I don't know any more about human interactions than anyone on this talk, but I maybe know more about the science of climate and radiation transfer. So during that summer, we had a highly classified visit from some Air Force officers. And this was the early days of Star Wars and the Strategic Defense Initiative. And President Reagan, when he took office, discovered that his only option if we were to be attacked by the Soviet Union was to commit suicide. We would launch hydrogen bombs onto Moscow and St. Petersburg, Leningrad, then every city in the Soviet Union, and we would all die together. And so that was our policy. It was called MAD, Mutual Assured Destruction, and it was certainly MAD. And President Reagan really didn't like that very much and didn't want to do it. So he said, well, let's figure out some way to defend ourselves if we're attacked so we don't have to commit suicide. And that was the birth of the Strategic Defense Initiative. So at that time, if you had any idea that might help to protect the U.S. against a missile attack, people were interested and wanted to hear about it. And one of the ideas was to shoot them down with high-power lasers. And missile warheads are pretty tough. They're designed to come through the atmosphere, red hot from the heating of the atmospheric friction. But if you put a megawatt of laser power on them, you can still deflect them, and keep them from reaching their target. And so people knew how to make megawatt lasers on the ground where you have plenty of power and cooling water and everything needed to make a laser of that power. But you had to get that laser beam through the atmosphere to the target. And so if you send a laser with a megawatt of power up through the atmosphere to an incoming missile, when the radiation reaches the target, instead of being focused on the missile, it's broken up into hundreds of little speckles, like the speckles you see if you've ever been in a laser lab. And none of these have enough power to cause much damage to the missile, so it doesn't work. And the reason for this speckling, this breakup of the beam, is the little patches of cold and warm air on the path between you and the target. So the laser beam runs a little faster in the warm air, a little cooler in the cold air, and as a result, it does not focus to a nice point, but it's as though it were going through a shower glass curtain, and it's all spattered out and does no damage. This was a problem that was well known to the astronomical community at that time, and they knew you could solve it if you could measure the distortions, and you can if you have sufficiently bright star. You can measure these warm and cool patches, and you can deform your observing mirror in such a way that it exactly compensates for the deformation of the atmosphere. So after one bounce on this deformed mirror, they call it a rubber mirror because you can squeeze it, press it, and expand it. The bounced wave is perfect again, and if you're an astronomer, you get a nice sharp image of a star. And if you're trying to defend against missiles, you put all the power of the laser onto the missile, and the missile is defeated. So at this meeting, it was clear that you could correct the laser if you could only have a star in the direction of the missile. But there are only 4 or 5 stars bright enough in the sky to provide enough light to do this correction. And astronomers had done that, and they showed that it worked. And so during the meeting, I said, well, I know how to make an artificial star anywhere in the sky, including the direction we're being attacked from. And there's a layer of sodium atoms at about 100 kilometers. And if you shine a sodium laser onto that layer, the sodium atoms scatter efficiently enough that you can get a very bright star, as bright as any other star in the sky, and use that yellow light to do the correction. So there was general disbelief. These were Air Force officers. They'd never heard of this, but to their credit, they went back to Washington and did due diligence. And at the end of the summer, they were back and they said, well, we don't see anything wrong with this idea. Maybe it will work. It doesn't sound possible, but we're empowered to try it out. And so they spent several $1 million building a sodium laser. They built a secret observatory in the desert south of Albuquerque, New Mexico. And I was getting quite nervous because of all this money being spent on my half-baked idea, although it was more than half-baked. I put in all the numbers. I was pretty sure it would work. But I can tell you I was very relieved when they turned everything on, and it did work the first time. So that was how I got to have a lot more interactions with Washington. So this was highly classified, but in the classified world, lots of people knew that I knew how to solve problems. And so I was invited to Washington for this job or that job because many people trusted me as a scientist that wouldn't bullshit. So now let's take a little time and talk about the science. I would guess that not everybody listening to this clip is a propeller-headed, techie scientist, but some of you maybe are. And so I will try and keep this short. But the first thing to know about the Earth is it doesn't have a single temperature. The rap on CO2, on carbon dioxide, is that it will boil the Earth. Even the head of UN is talking about global boiling. I mean, I never heard of anything so silly. But anyway, what are you supposed to do if you don't have any technical background? With the head of the United Nations tells you the seas are boiling. Who are you going to believe? Your lying eyes or the president of the United Nations? Of course, the seas aren't boiling; they will not boil. But the Earth doesn't have a single temperature. It has a temperature that varies from room to room in your house, inside, outside, and especially if you go up in altitude, the temperature drops very rapidly. When I went to Australia, I had looked up the temperature at their highest mountain. It's not terribly high, but there's a hotel there, Hotel Kosciuszko, at 1.5 kilometers altitude. And when I gave the talk in Melbourne, I said, on average, that's 10 degrees colder than Melbourne. I looked up temperature records for both places. And so that means that the temperature drops 10 degrees for every 1.5 kilometers. You divide that, that's a 6.6 degrees centigrade per kilometer. And that's a pretty good number that you find all over the world in the lower troposphere, where you have a lot of moist air that's in contact with either the oceans or the moist ground. And it drops even faster when you run out of water at higher altitudes. It approaches 10 degrees per kilometer. But it's important in trying to understand how greenhouse gases work that you remember that a big part of the physics involves this temperature drift, temperature decrease I'm showing you now, the temperature lapse rate. When you get above, say, 11 or 12 kilometers at latitudes where we live, the temperature stops dropping. And that's because at that altitude, the rising and falling parcels of air of the convective troposphere stop, and there's very little convection above 10 kilometers, say 30,000 feet, 35,000 feet. And that's why jet planes like to fly there, because it gets them out of the weather and you tend to have a much smoother flight. And so they're designed to fly just above the tropopause where convection stops, and where, with a few unpleasant exceptions, you get a nice smooth ride from start to finish. If you go even higher, temperature begins to rise again because of the ultraviolet heating of ozone in the stratosphere. The sun, of course, emits radiation of many wavelengths, including a little bit in the ultraviolet, and that causes substantial heating. In fact, at the stratopause at about 30 miles above us, the temperature is not much less than it is at ground level. So it gets quite warm in the upper stratosphere. So here are the basic facts that everyone should remember. The Earth is really heated by sunlight. We get a little bit of we get a little bit of heat coming up from the interior of the Earth, but it's thousands of times less than the amount we get from sunlight. So to first approximation, the sun is the only thing that counts. And the sun radiates relatively short wavelength light. A lot of it is in the visible that we can see, or the near infrared, which we can almost see, and a little bit is in the ultraviolet. I mentioned that in connection with the stratospheric heating. And so if you don't get rid of that heat, the Earth would indeed boil, just like the president of the UN says. But we do get rid of the heat by radiating long waves, thermal radiation, back into space. Space is very cold. Its temperature is, several hundred degrees below zero on the Celsius scale. So it's easy to get rid of heat into space. And the way we get rid of it is we send out thermal radiation. It's the same sort of radiation you see if you go to a trendy outdoor restaurants and you sit under these radiators. They glow with a dull red color, but you feel nice and cozy from the infrared radiation coming down from that black radiator. It's heated with natural gas typically. Now, I said this is long wave radiation, and so it involves more than one wavelength. There are lots of wavelengths. So what I'm going to do now is show you the spectrum of the thermal radiation from the Earth to space. This is the radiation that cools the Earth. So here on the right column, you can see three spectral curves. Here's observation over the Sahara. Here's over the Mediterranean a little bit further north, and here's over Antarctica. You notice the scales are different, the vertical scales are different. So not surprisingly, the Sahara radiates a lot more thermal radiation to space than does Antarctica. Look at the left-hand scales. And what I've plotted here, the vertical axis is intensity of radiation in milliwatts per square meter down here, an intensity unit in the caption. And on the horizontal scale is the spatial frequency of the radiation, the number of waves per centimeter. So CO2 peaks, this is CO2, at about 667 waves per centimeter. And here is ozone, maybe 1,100 waves per centimeter. And so what you see is a spectrum that has a lot of noise, seemingly noise. It's not noise at all. It's the absorption by various greenhouse gases in the Earth. And it's quite different for different latitudes on the Earth. And CO2, which is the cause of this gap here, over most of the Earth actually decreases radiation to space compared to neighboring frequencies, but over Antarctica, it actually has the opposite sign. So over Antarctica, CO2 is a global cooling gas, but over most of the Earth, it's a global warming gas. Now, the reason I'm showing that is that this particular curve, you can calculate to a few percent. Yeah, you get it right if you do the calculations right. So on the left are calculations that William Van Weingarten and I did. This paper here summarizes them. And you can hardly tell the difference between the calculated curve and the observed curve from satellites. Calculated, observed, calculated, observed. So the point of showing you this is the only thing that we seriously calculate are radiation fluxes going away from Earth. And we're really good at that because what we calculate is what's observed. We don't compare our calculations to other groups, competing groups. We compare it to what's observed from satellites, and we do very well. Now, on this left-hand set of curves, which are supposed to match those on the right, and they do, you can also see a dashed red curve, and that's the Planck spectrum. So if the Earth had no greenhouse gases over the Sahara, you took them all away, the radiation going to space would be this nice, smooth, dashed red curve, not this jaggedy curve here. So the effect of greenhouse gases is to diminish the radiation to space from the area under the dashed red curve to the area under the black curve. So we'll talk more about that, but you can see it's a fairly substantial effect at the Sahara. And in fact, over most of the Earth, the exception is Antarctica, where greenhouse gases actually help the Earth radiate a lot more than it would if there were no greenhouse gases. And the reason for that is that this is CO2 up in the stratosphere, and the stratosphere is warmer than the surface of the Earth over Antarctica. Over Antarctica, there's a huge temperature inversion because the surface radiates into the night sky so efficiently that it cools way below the temperature of the atmosphere above it. So Antarctica is always an exception. Okay, so now I'm going to say a little bit more about how you calculate those curves, because they're a key part of this. If you don't believe we're calculating the curves correctly to a few percent, and their differences to much better than that, then what I'm going to say shouldn't impress you. But I can assure you that we know what we're doing on the calculation. So for the propeller heads in the audience, you do the calculation by solving this humongous equation here. This is called the equation of transfer, and it actually was not invented by climate scientists. It goes back to the early days of astrophysics, when people were trying to understand how do you get radiation from the center of a star where thermonuclear reactions are going on out to the surface and into space. The star itself has to cool too, and much of the heat transfer is due to radiation. And the radiation flux is called I, the intensity. I should call it intensity as opposed to flux. And it changes. So on the left side of this equation is the rate of change of the intensity with altitude. C is the altitude. And it changes for two reasons. First of all, it's absorbed by greenhouse gases or particulates if they're clouds, and that's described by the monochromatic attenuation rate, alpha. This has units of inverse length. It's the E foldings per length. And this is the hard part of this calculation, is that alpha is so complicated as a result of greenhouse gases that you have to do this calculation for many thousands of different frequencies to get the right answers that agree with what satellites observe. And I'll say a little bit more about how you calculate alpha later, but this is the hard part. How do you calculate the attenuation? Mu is the direction cosine. Of course, radiation goes straight up, and some of it goes up at 45 degrees or 60 degrees, and you have to account for all angles coming out of the Earth. So this calculation also has to be repeated for different zenith angles of the upcoming radiation. Then when you have clouds, it's you have to include the fraction of radiation that's scattered as opposed to being absorbed and converted to heat. So this is called the single scattering albedo. We put a tilde over it. I think this goes back to Chandrasekhar or something. It's a common symbol for single scattering albedo, but it's the fraction of photons that are scattered into different directions as opposed to being absorbed and converted to heat by, say, a CO2 molecule or a droplet of water. And then finally, there's this humongous integral over here. So this is an integral differential equation. It's a very hard equation to solve. And but fortunately, with no clouds, since it has the single scattering albedo, and greenhouse gases don't scatter at all, so the greenhouse gas single scattering albedo is 0. For clear skies, you drop the last term. So when you read papers about radiation transfer, people like to talk about clear skies because they don't have to handle this miserable last term here, which is quite difficult. But you can do it. William Van Weingarten and I are working on this now, and we know how to do it efficiently and accurately. Finally, another parameter here is the Planck intensity. We looked at the Planck intensity view graph or two ago. It was that dashed red curve, and it's the black body radiation. That was the origin of quantum mechanics. So this is a very famous formula. It's the first formula of quantum mechanics. And what Planck showed was that you could solve all of the horrendous problems of pre-quantum mechanics physics if you assume that energy had to be quantized. So a photon can't have any old energy. It has to have an energy which is its frequency times Planck's constant. If you're using spatial frequency, you have to multiply the spatial frequency by c. So this is speed of light here. But this is a very, very famous curve. And you can read more about this at these links here if you'd like to dig in. But this is really all I want to say, and I apologize to the non-propeller heads in the audience. I mentioned that it's hard to calculate the attenuation, and this is the reason, because this is frequency again, spatial frequency, and these are the absorption cross-sections for the various greenhouse gases in the atmosphere. Most important of all is water vapor, but CO2 is second. Ozone is probably third, quantitatively. Nitrous oxide and methane are quite a bit less. They're sort of at the level of a few percent. But each of these gases has many tens of thousands of individual absorption lines, each of them represented by one of these colored points here. So, for example, in the case of water vapor, there are several 100,000 of these blue points. In the case of CO2, there's about 100,000 red points that we take into account. And so these cross-sections are measured in something called the line strength. So the vertical axis, note it's logarithmic, but the vertical axis is the line strengths of the different absorption cross-sections. It's actually the integral of the cross-section, the area under the cross-sectional curve with respect to frequency. So what makes this hard is adding the contributions of all these many, many lines that are on this picture to the single absorption coefficient, alpha, that we were talking about. And you have to do the calculation at many different altitudes. It's not the same at the surface as it is at 5 kilometers or 10 kilometers. And so this really chews up computer time if you're not careful and efficient in the coding. All of these, by the way, have Planck curves on them. So the black curves here are Planck curves. So the right-hand scale is the scale for the smooth black curve. And so this says, for example, in the case of CO2, this band here, this is actually about 4 microns, if you convert this to wavelengths. This is the one that's used by, for example, CO2 meters that you use to measure CO2 in a room or a building. But it's irrelevant for the thermal radiation of the Earth, because all of the absorption lines lie well outside this black curve, which is the kind of radiation the Earth emits. The frequency is too high to make any difference. The same thing happens for many of the bands of nitrous oxide, some of the others. Okay, now let's dig a little bit deeper. And I'm coming back to the curves I already showed, but in much more detail. And so what I'm showing now is the Planck curve, which is this blue smooth line. The black jagged line is the curve including greenhouse gases, and I like to call that the Schwarzschild curve, because it was Schwarzschild who showed how to do that calculation. In fact, it was Schwarzschild who invented this equation here. This part of the equation, leaving out the scattering, is due to Schwarzschild. So Schwarzschild was a very important figure in physics. He was the first to find an analytic solution to Einstein's general theory of relativity. In fact, it was done in 1915, was when he was on the Russian front in World War I. And he died on the Russian front. It's very sad. He was such a talented guy. It was not because of injuries. It was because of a hereditary autoimmune disease that worsened very rapidly under the poor conditions of the front lines there on the Russian front. But we lost a great man with Karl Schwarzschild. And Max Planck, who lived much longer, is another great hero of physics. In fact, should be a great hero of humanity. He invented quantum mechanics. He was a completely honest man. He remained in Germany throughout World War II. He refused to collaborate with the Nazis. He helped their victims in every way he could. His son was executed by the Nazis, supposedly for being in a plot against Hitler, and it's lucky they didn't execute him. It's only because he invented quantum mechanics that he didn't. But now let's come back to physics. And so the black jagged curve is the Schwarzschild curve, is what the Earth actually radiates to space. And I showed you a few graphs ago that although this is a calculation, what you calculate is what you observe. So you should take this seriously. Now, the important point here, this is the most important slide of this talk, the most important view graph, is that if you double CO2 concentrations, you get this red curve. And the red curve is identical practically to the black curve. So the only part of the spectrum where there's a little bit of difference is in the middle of the CO2 absorption band here. And here's another tiny difference here and here. But you can hardly see the difference. And so the message here is if you double CO2, you reduce the area under this curve, the radiation going to space, from 277 watts per square meter, which is what it is today, maybe a little less because this is for 400 parts per million. It might be 425 today. You reduce that to 274, only 3 watts per square centimeter for doubling CO2 out of roughly 300. So it's a 1.1%. I will just say 1%. It's a 1% effect. So this is important. Let me repeat it. A 100% increase of CO2 from 400 parts per million to 800 parts per million causes a 1% decrease of radiation to space. You know, that's a pretty poor rate of return, isn't it? And what this is telling you is that CO2 is not a very potent greenhouse gas. You can increase CO2 a lot and nothing happens, or almost nothing happens. Of course, something happens, but it's very small. Okay. We're not worried about flux. We're worried about temperature. So there are really 2 steps when you're calculating greenhouse warming. The first is to calculate the change in flux, which is this temperature here. And as I mentioned, you can calculate this very accurately to within percents. And the second stage is to use that change in flux to calculate a change in temperature. And so that's where all the mischief is. It's how do you go from a change in flux to a change in temperature? So I'm going to show you the first order way of doing that calculation, and that's probably the correct way. But again, there are 2 famous people associated with the key equation. This is the famous T to the 4th law, the Stefan-Boltzmann formula, which says that the flux, F for flux, goes as the 4th power of the absolute temperature. Then it has a universal constant, the Stefan-Boltzmann constant, which is, you know, a combination of Planck's constants and, you know, Boltzmann's constants and fundamental constants, and then something that depends on the body itself, the emissivity, epsilon. Okay, so greenhouse gases affect epsilon, the emissivity of the Earth to space. And so I just showed you in the previous view graph that for cloud-free Earth, epsilon, which is the ratio of the 277 watts per square meter that actually is radiated by space to the 394 watts per square meter, which is the area under the blue curve, that ratio is about 70%. So Earth's emissivity is 0.7. And Stefan-Boltzmann constant is fixed. Really is a constant. And the average surface temperature of the Earth is 288.7 Kelvin. It's about 60 degrees Fahrenheit or 15 degrees centigrade. So the emissivity is less than 1 because of the greenhouse gases and because of the vertical temperature variation that I showed you, the temperature lapse rate. I should say, by the way, that if there were no temperature lapse rate, you could add all the greenhouse gases you want. It would make no difference to the radiation to space. So the temperature profile of the Earth is very important in calculating greenhouse warming. So doubling CO2 is a 1% decrease of radiation to space. So from, again, I'm talking to the propeller heads. The flux can't change because you still have to get rid of the flux that's heating the Earth from the sun. So as you change the emissivity, if the emissivity goes down by 1%, the temperature has to go up a little to compensate. And so the simple calculus computation of this says the temperature increase has to be 0.25%, 1/4 of the relative increase of the emissivity, decrease, I guess, of the emissivity. So radiation to space decreases by 1%, temperature has to increase by 0.25%. So that's the bottom line. 0.25% increase in temperature, absolute temperature from doubling CO2. Well, that's, you put in the numbers, you take 0.25% of the average absolute temperature of the Earth, you get 0.71 centigrade. Very small number. You can't perceive 1.71 centigrade. You know, your air conditioner or your heating system will not trip if the temperature changes by 0.71. You know, it controls temperature typically to about 2C. So this is something you can't even feel. And yet we're being asked to give up our liberties, to spend trillions of dollars to prevent an increase in temperature of 0.71 C 100 years from now when we manage to double CO2. It takes a long time to double CO2. This is for doubling. Okay. So here's the problem. 0.71 C is not enough to justify climate emergency. You know, you keep reading about the emergency, you look around again, who are you going to believe? The mainstream media or your lying eyes? You know, I don't see any emergency. There's obviously not one. And you don't even see it in the data, the quantitative data. So if this is true, why do we have the IPCC, or why do we have enormous departments of climate science in all the major universities of the Western countries? And, you know, why do we have tens of thousands of people flocking from one climate conference to another at huge expense, emitting enormous amounts of CO2 as they jet around? There's no reason for it at 0.71. So you have to do something, and what the community has done is they've invoked huge positive feedbacks, mostly from water vapor, that's the favorite, clouds, whatever sounds plausible, to increase the predicted warming to 3 degrees centigrade or more from doubling CO2. And so these positive feedbacks, I like to call them affirmative action for CO2. CO2 is not a very good greenhouse gas, you know, and so it needs some help. They appear to be threatening, and the help is the positive feedback. Now, there's a problem. This is a natural system, the climate we're talking about, and for most natural system, feedbacks are negatives. This is so widespread, it's even got a fancy name, Le Chatelier's principle. So this is the French chemist, Le Chatelier, and here's a statement of his principle from, I think, maybe Wikipedia, I'm not sure. When a simple system in thermodynamic equilibrium is subjected to a change in concentration, temperature, volume, or pressure, number one, the system changes to a new equilibrium. And number two, this change partly counteracts the applied change. So number two states that the feedbacks that cause the change, the feedbacks are negative. They try to make the first answer you calculate smaller, not bigger. So those of you who suffered through this without a technical background, this was the last quantitative transparency I'm going to talk about. So now I'm going to summarize this with a picture that doesn't require differential equations or anything like that. And so what we say is the CO2 effects are saturated. Let me go back and point them out to you again. So here is black is current CO2 levels, 400 parts per million. Red is 800 parts per million, doubled. And so physicists, spectroscopists like to say that the CO2 band here is saturated. You know, you add more, it almost doesn't make any difference. It's done all it can. It's saturated its abilities. And we're familiar with situations like this. Here is a quite close analogy. If you have a barn and you want to paint it red, you can put a nice coat of red paint on here. And then you might think, well, you know, I've got lots of money. I want to show how rich I am. I'm going to put 2 coats of red paint and make it even redder. But if you put a second coat, it won't make any difference, because a good quality paint, 1 coat is enough, and its color effect is saturated, just like the saturation of the CO2 band. So a barn with 1 coat and a barn with 2 coats of red paint look exactly the same. And that's also true of the color of the Earth in the thermal infrared. This is like the color spectrum of the Earth. And if you double CO2, if it looked red before, it will look red after, and you will hardly be able to see the difference. There is a tiny difference. Let me say it's not 0, but it's only 1%. It's a 1% effect. You wouldn't be able to see a 1% effect in the redness of this barn. Now let me move on to a second issue I want to talk about before I end, and that is that not only is CO2 not very potent in changing the climate, but it's just the opposite. It's very potent with respect to benefits to agriculture and forestry. So this is a field of soybeans. When I check with my academic colleagues, almost none of them have ever been on a farm, so they have no idea what this is. Some of them, when I ask them, they say, well, is it marijuana? But it's soybeans, and it's growing very well. And part of the reason it's growing well is because of more CO2. So this is what happens in the laboratory if you add CO2 to growing plants. This is a common weed in New Jersey, velvet weed. And if you grow it at the levels that prevailed during the last glacial maximum, which got down to around 150 parts per million, a little bigger than that, the plant can just barely grow. So if you go much below this, it sprouts and it dies. Pre-industrial levels, 270, say the year 1800, 1850, around that time, the plant grows pretty well. If you increase it, it grows better. If you increase it more, it grows better still. And every experiment you ever do with plants in the laboratory or in the field show that plants grow better with more CO2. So CO2 is very good for photosynthetic life on Earth. And there are 2 main reasons for this. First of all, plants need less water if there's more CO2 in the air. So that's reason number 1. That's probably the most important reason. But you can also add CO2 to plants that grow in greenhouses, and that was the experiment that we just looked at. This was grown in a greenhouse. And it still grows better in a greenhouse with more CO2, where the greenhouse, there's no problem with water. You provide all the water the plant needs. And the problem here is more subtle. It's because most plants, C3 plants, lose about 25% of their photosynthetic potential because of something called photorespiration. And this is a fascinating issue that goes back to the beginnings of life on Earth. And at the very beginning of life on Earth, an enzyme was invented. In fact, let me skip to the next slide. We'll come back to this, called RuBisCO. So this is RuBisCO. It's a big, complicated protein. It's the most abundant protein in the world. So if someone ever asked you, what's the most abundant protein in the world, you know the answer. It's RuBisCO. There's more protein here than there is in all the beef in Argentina, because it's the protein that all photosynthetic organisms need. And not just photosynthetic organisms. You find the same enzyme, in the deep, dark waters of the oceans near oceanic vents, where chemosynthesis, it provides the energy for driving this enzyme, the ATP, So this enzyme is supposed to take CO2 and attach water to it and add it to sugar molecules. These are simple sugar molecules here. But it was designed at a time when there was no oxygen in the air. So if there is a lot of oxygen and little CO2, which is the situation today, about 25% of the time, instead of grabbing a CO2, the enzyme grabs an oxygen and it produces things that are actually toxic to the plant. I won't go into the detail, but these break down into nasties like hydrogen peroxide, ammonia. And so the plant has to spend a lot of effort to detoxify this oxygen step here, this 25% step. And so if you increase CO2, it's more likely to grab a CO2 when it's photosynthesizing and less likely to grab an oxygen. So that's the main reason that greenhouse gases, real greenhouses, not greenhouse gases. It's the main reason that plants grow better when you add CO2 to greenhouse gases. Now here is a typical plant leaf. This is an elm leaf, and it has a little hole in it. Of course, there are many, many holes in it. And the reason for that hole is to let CO2 diffuse into the leaf from the air, get into the liquid, biochemical factory of the leaf, and be converted to sugar with the aid of RuBisCO, the enzyme we just talked about. And so you need CO2, you need water, and you need sunlight to provide the energy. If you're a vent creature, you don't need sunlight, but you do need chemicals to oxidize to provide the driving force, the chemical driving force, the ATP for this reaction. The problem, and here again, I want you to remember this carefully, is that for every CO2 that diffuses in from the air, there's not much CO2 in the air. Typically, 100 water molecules diffuse out. So a photosynthesizing plant has a engineering trade-off problem. It has to put holes in the leaf to get CO2 to grow, but the holes make it leak water vapor out into the open air. And so the plant really doesn't like to have these holes. And plants aren't stupid. If you increase CO2 levels, the plant simply grows leaves with fewer holes and doesn't open the holes as widely as with the lower CO2 levels. And so if you look, for example, at an elm leaf in a herbarium from 1850, and you count the stomata on the leaf, you'll find that there are more stomata in the museum specimen than there are from a leaf that you would harvest from a tree today. And that's because of the increase of CO2 in the atmosphere. So all plants are doing better today than they did 100 years ago or 200 years ago because they don't need as much water as they used to need because they don't have many leaky stomata in their leaves. They don't need as many stomata. There's a second type of plant. It's not nearly as abundant, but several of our most important food crops are C4 plants. This is called C3 because, as you remember from the picture I showed you of RuBisCO, the first sugar molecule has 3 carbons in it. So 3 carbons, C3. There's a C4 plant, and the typical examples are U.S. corn, maize, for example, or sugarcane. And these are designed to cope with the photooxidation I mentioned, the RuBisCO poisoning from oxygen. So they have a more complicated scheme of transferring CO2 into a region where oxygen is kept out. And then that avoids the photorespiration, but at the cost of quite a bit more biochemical machinery. So the capital investment is more for this type of leap than it is for this type of leap. And so you would not use this type of photosynthesis if there were plenty of CO2. And so as CO2 increases, this type of C3 plant will begin to outcompete C4 plants. C4 plants aren't going to go extinct, but they will not be nearly as they will not enjoy as much advantage as they used to enjoy. And here's an example of the greening of the earth as a result of CO2. This is from Donahue. You can look up this reference, but typically, and this was from 1982 to the year 2010. And what you see is that the entire earth is getting greener. You know, you hear about desertification because of climate change. It's just the opposite, actually. Deserts are shrinking. They're not getting bigger. And that's because plants can now live at the edge of deserts where it used to be too dry, to survive. But now plants don't need as much water because of the fewer stomata. And so they're growing. Look at the Western Australia, which is very dry. Look at the Kalahari Desert here in Africa, the Sahel, Western United States. Everything's getting greener. So why would you want to call CO2, the molecule that makes this happen, a pollutant? It beats me. Okay, so let me try and finish up now. And what I'm going to say from now on, I have no more expertise than anyone in the world. This involves human motives, human behavior. I've studied human behavior all my life, and I still don't understand it. It's a lot easier to solve an integral differential equation than it is to solve why humans do what they do. But here are some problems. They're noble lies. They're political lies. There's ignorance. There's stupidity and greed. So I'll talk about each of these briefly. So noble lies is a concept that probably goes back before Plato, but it was first described clearly by Plato in his Republic. And here's what Wiki says about noble lies. In politics, a noble lie is a myth or untruth, often but not invariably of a religious nature, knowingly propagated by an elite to maintain social harmony or to advance an agenda. The noble lie is a concept originated by Plato, as described in the Republic. So, I never paid much attention to Plato, but I went back and I read his sections on the noble lie, and this is a pretty good summary of it. And certainly a part of the alleged climate emergency is a noble lie. You can read about this in the early papers, like the Club of Rome describes their search for some enemy, that all humanity could focus on, so we wouldn't be fighting each other. And so they apparently have decided that the enemy is CO2. It's a crazy choice because, of course, CO2 is beneficial to life on Earth, to all life on Earth, not just humans. But part of what we're witnessing is a noble lie. Then there are political lies. It's the best definition I've ever seen is by H.L. Mencken, one of my favorite curmudgeons, the early 1900s. He says the whole aim of practical politics is to keep the populace alarmed and hence clamorous to be led to safety by menacing it with an endless series of hobgoblins, all of them imaginary. So, that's what's happening also with the climate emergency. The mainstream media, talking heads continue to paint these terrible pictures of the Earth, global boiling. The head of the UN says it, none of which is true. And if you're a reasonably cynical human being, you're not terribly upset by this because you just assume that lots of people lie. These just another lie. But if you're a child, it can often ruin your life. You read about children committing suicide because of the threat of climate change. They will not live to adulthood, so might as well die now. It's unconscionable what we're doing to our children with this nonsense, with lives, basically. It's terrible. And there's ignorance. Lots of people are well-meaning. I have many friends who firmly believe that the end of the world is nigh, from climate change. They haven't started riding bicycles or given up their SUVs, but they're absolutely certain that it's going to happen. So they're ignorant. And this is an example of ignorance. Jan Hus was one of the early reformers of the church in Europe, in Czechoslovakia. And at that part of the church, maybe more, was quite corrupt at that time. And for pointing that out, this was 100 years before Martin Luther. Jan Hus was burnt at the stake. And when they burnt him, it was a wet day. It had been raining, and so the wood was wet. It wouldn't hold a flame. And so a poor old woman, could barely afford anything, came up with a big load of dry brush, which she dumped at the feet of Hus, and it was nice and dry. So when they put the torch to the dry wood, it flared up, and he was burnt to death. But his comment was, "Sancta simplicitas," holy innocence. So the old woman was not evil. She thought she was doing God's work, by burning this terrible heretic at the stake. But she was ignorant. And so we see a lot of that with climate today, So let me move on to another interesting cause. I never used to take this all that seriously when I first heard about it, but Dietrich Bonhoeffer was one of the brave German clergymen who remained in Germany throughout World War II and consistently opposed the Nazi atrocities in the 30s. He was quite outspoken. He had a chance to come to America and save himself, or to England, but he went back to Germany and spoke out, and of course was eventually arrested, and he was executed before the Americans could save him, or the Russians. I don't know who was closest, but they didn't make it. But here he decided that really the biggest problem is often stupidity. It's not malice, but stupidity. And here's his comment: against stupidity, we can have no defense. By the way, if you read this in German, stupidity is not the greatest translation. In German, it's Dummheit, dumbness. And I think dumbness might have been a better translation, but I will read as it was translated. Against stupidity, we have no defense. Neither protests nor force can touch it. Reasoning is of no use. Facts that contradict personal prejudices can simply be disbelieved. I mean, the UN says the world is boiling, the seas are boiling. Who are you going to believe? Indeed, the fool can counter by criticizing them, and if they are undeniable, they can just be pushed aside as trivial exceptions. So the fool, as distinct from the scoundrel, is completely self-satisfied. In fact, they can all easily become dangerous, as it does not take much to make them aggressive. I'm sure many of us experience, you sit down for dinner and you express some doubt about, whether there really is a climate emergency, and you're lucky if you're only expelled from the house. For that reason, greater caution is called for than with a malicious one. So here's an example an old example. This is a letter from Galileo to Kepler. My dear Kepler, I wish that we might laugh at the stupidity of the human herd. What do you have to say about the principal philosophers of this academy who are filled with the stubbornness of an asp and who do not want to look at either the planets, the moon, or the telescope, even though I have freely and deliberately offered them the opportunity 1,000 times? Truly, just as the ass stops its ears, so do these philosophers shut their eyes to the light of truth. This was written in 1610. Actually, Galileo was lucky. A little bit earlier, Bruno was actually burned at the stake for, promoting the same ideas as Galileo. So then there's the good old motive that we all understand, greed. This is one of my favorite quotes from the great Russian writer Alexander Pushkin. It's from a adventure novel for adolescents he wrote from Dabrowski, but it says, if there should happen to be a trough, there will be pigs. And, if you're in academia, you see that, or if you're in industry, sustainable development, there are plenty of pigs at the trough, and the government is dishing out billions, hundreds of billions of dollars, to save the planet, and there are lots of takers. So why are we having this talk? You've used it if you have the patience to sit here for an hour and listen to this, or I've had the patience to talk for an hour. The reason we're doing this is there's no question that the finale of this latest mass popular delusion will be disaster. This is the net zero finality. It will be a car wreck, a train wreck, whatever you call it. And I can't do better than quote from Dietrich Bonhoeffer again. If I see a madman driving, let's see, I was too hasty here. If I see a madman driving into a group of innocent bystanders, then I can't simply wait for the catastrophe and then comfort the wounded and bury the dead. I must try to wrestle the steering wheel out of the hands of the driver. So those of you who are listening to this, please join me and Tom and other people of goodwill to try and stop this disastrous dash into perdition. So thank you very much.
Okay, thank you very much. That was absolutely brilliant stuff. Thank you for taking the time, because a lot of people are going to be watching and listening. So thanks again. Before you leave, do you want to say anything about your founding of the CO2 Coalition?
Well, yes, let me say that I had a lot to say about quantitative facts. And if you would like to learn more, please check out the website of the CO2 Coalition. It's very easy. If you go to Google, just type in CO2 Coalition, and our website will pop up. And you can find lots and lots of good stuff there about climate. We do try to exercise some quality control, so I think most of the stuff there is quite sound. Every now and then something gets through, but most of it is good. So the CO2 Coalition is a group of a little bit over 100, mostly scientists and engineers and economists who are concerned about this wreck that we're looking at now, which will be the end of the climate emergency delusion. And they talk to their friends, they write op-eds, they take every opportunity to try to explain to our fellow citizens what a ruinous course we're on right now, and to educate them. So if you're interested, do look. If you're a scientist or engineer interested in joining, please write me. I'm at Happer at Princeton.edu, and we'll try and get you aboard.
All right. Very good. Any other points you'd like to make before we finish?
No, I think I would like to thank you, Tom, for doing this. It's a lot of work, and I you're not compensated for doing this, I don't think. So it's really and same for me. We do this for nothing because we're worried about our society, about our children and our grandchildren, and so those of us who are doing this, this is really pro bono, pro bono publico, for the good of the public. And I think that's a worthwhile way to spend part of your life. And so I'm happy to do it. And I hope lots of other people will join me. And I'm quite sure we will eventually win, because when this wreck happens, that will be the end of the climate delusion. But it would be better to end it in a less dramatic way.
All right. Thank you very much. I'll let you go. Will Happer, thanks for your great work.
Yeah, thank you. Bye-bye.